Okay, so let me welcome you to this fifth lecture of our course on reinforcement learning. And after 4 lectures that were sort of overview and big picture type of lectures, we're going to get a little bit in more depth on various topics. And we are going to start with rollout today, first for deterministic problems, and then for stochastic problems. So here's our outline. We start with the rollout for finite state deterministic problems like the ones that we have discussed so far with the traveling salesman problem and so on. Then we're going to discuss an important question, whether the rollout algorithm improves on its base heuristic. That's what we mean by the cost improvement algorithm, whether we're getting cost improvement through rollout. Then we're going to discuss various variants and extensions of the rollout algorithm that are aiming for greater generality and greater computational efficiency. Then we're going to take a break and go into stochastic rollout algorithms and the method of Monte Carlo Tree Search. And I'm going to use here a video clip from last year's course. And finally, we're going to talk about rollout for problems that involve infinite spaces, infinite state space and infinite control space, in which case the finite state methods that we gave earlier are very cumbersome. And we're going to discuss alternative methodologies that will also lead into the model predictive control design schemes that we're going to discuss in more detail in the next lecture. So the one thing that I want you to remember about the rollout algorithm is it's a special case of approximation in value space, our general umbrella scheme for online generation of controls. We have one-step look-ahead approximation value space and the multi-step look-ahead. I'm showing here the multi-step look-ahead version. And the rollout algorithm basically is a special case of this J tilde. J tilde is the cost function of some base policy. So we have all the other aspects of approximation value space. We have at a given state, xk, we do this minimization that involves the first L steps and the future stages as represented by the base policy and its cost function. And we do this minimization and we obtain the rollout control that we apply at state xk. And a rollout policy, which we denote by mu tilde k of xk, is just this control uk. Of course, this minimization involves a finite horizon, stochastic problem. We minimize over uk, the first control at the state that we know, and the policies for the future states that we do not know, cannot predict because they involve randomness. We get this thing here, we throw away the mu stuff, we keep UK, and this is the rollout control that we apply and defines the rollout policy. And of course, we have one-step look-ahead minimization, multi-step look-ahead minimization. I'm showing here the multi-step case. In either case, we obtain a rollout policy, this mu tilde, which will use this name. It's a rollout policy. It's an honest to goodness policy. At every state, at every possible state, it defines a control through this minimization. Now, there may be some approximations in this scheme. For example, the minimization here may be approximate. The expected value calculation may be approximate. We'll get into this in time. But an important approximation variant is truncated rollout, where this J tilde is approximated by truncation. simulation over a number of steps, and then taking a cost function approximation. So with all these approximation variants, starting from this base case, we cover a lot of ground, a very large part of approximation in value space. So now let's go into deterministic finite state problems. No expectations, no uncertain quantities. Why do we want to cover rollout, and why is it important for our course? Well, first of all, it provides options, important options for cost function approximation in the context of approximation in value space. So it's one possibility, and with its variations, quite a few possibilities. Then rollout is also a building block in the policy iteration algorithm, which is fundamental, primarily for the infinite horizon case. The policy iteration algorithm involves a repeated rollout, evaluating policies and then applying rollout, the rollout algorithm for policy improvement to obtain a new base policy and so on. Now, here are some reasons why it's significant. It occupies a significant position within the landscape of methods. First of all, rollout is the easiest method to understand and also the easiest to implement. Once you know your base heuristic or your base policy, then it's very easy to write a program to implement the rollout algorithm. Other methods are much more complicated. It's also easy to understand what's going on. There are no neural networks involved which are sort of opaque and you don't know what's happening. The other thing about rollout is that's very reliable. It's by far the most reliable method in reinforcement learning. Okay, with correct implementation, okay, because there are some pitfalls, but generally speaking, it's easy to apply and you can expect that it will work almost every time. In my experience over 25 years with all these reinforcement learning methods, I have found out that all of them are flaky, but rollout has never let me down. It has always worked for me. And I think this has been an experience that has been shared by many other people. So it's very reliable, simple, reliable. You can try it out and then you can try for something more ambitious perhaps, but it's a good place to start. Then it is very general. It applies to deterministic problems, stochastic problems, finite horizon problems, infinite horizon problems. It can be applied to just about any kind of dynamic programming problem. It has a connection to Newton's method, as we have discussed, because it's a special case of approximation in value space. An approximation in value space with one step look ahead or multi-step look ahead relates to Newton's method. So there is this connection to guide the implementation and the intuition. Okay, some special domains, like in adaptive control, where the system parameters change over time. And as they change, we estimate them using some kind of a system identification algorithm, for example. And then the method of indirect adaptive control takes the new parameters that you have estimated and then reoptimizes the entire controller based on these new parameters. Well, rollout provides a cheaper alternative to reoptimization, to adaptive control by reoptimization, namely adaptive control by approximate reoptimization that involves rollout. And that can be useful in some cases because this reoptimization can be very expensive in practice. There's also a connection with model predictive control. I mentioned this connection in one of my earlier lectures. Rollout following, truncated rollout following multi-step look ahead or one-step look ahead minimization It can be used to bring J tilde within the region of stability of the problem. Issues of stability are very important in model predictive control, how you pick J tilde so that it produces a stable approximation in value space policy, look ahead policy. That's a big question, and truncated rollout can help to bring the J tilde within the good region of stability. We may revisit this later in another lecture. Finally, rollout is a building block, a piece in many other reinforcement learning methods that are used in practice. Q-learning may involve using a policy to generate samples and also estimate cost functions at one point or another. Self-learning or approximate policy iteration, as it's called, it is a name more appropriate for our course, is similar. It involves repeated rollout. And the other methods, well, rollout plays a part. So all of these are compelling reasons. And because of the simplicity of the approach, we discuss it first in this course. Okay, so we'll start with deterministic rollout, deterministic problems and finite state. And we have gone through this figure before. We generate a state trajectory, one state at a time, one stage at a time. At the typical stage and state, xk, suppose we have reached the state xk, what we do is we consider all possible controls and we assume a finite number in this picture. And for every pair of state and control, we generate a Q factor, which is the cost of the transition using UK, plus the cost of the heuristic policy, starting from this state and going all the way to the end. The sum of the costs of this and of that is the Q factor of this control. And there are several of those Q factors. And what we do in the rollout algorithm, we select the control that has minimal Q factor. We minimize over U by exhaustive comparison of all the controls. Then we move to the next state and do the same thing. Consider all controls, run the heuristic from the end of each one, and so on. There are also multi-step look-ahead versions of this, where we look multiple steps ahead. The big question here is whether rollout is cost improving. What do I mean by that? If you run the base heuristic from the initial state x0, you obtain a certain solution, a certain state and control trajectory with certain cost. If you run the rollout algorithm, go all the way to the end, you generate a different state trajectory and a different control trajectory. Will the rollout trajectory have smaller cost than the trajectory corresponding to the base heuristic? That's what we mean by this question. Is the rollout improving the cost of the base heuristic starting from x0? That's an important theoretical question as well as a practical question. So that's what we're coming to now. The first thing to note is that cost improvement does not come automatically. It's very easy to construct base heuristics that do not have this, for which the rollout algorithm does not have this cost improvement property. There must be some special condition that should hold in order to guarantee this cost improvement property. And there are two such conditions. One is called sequential consistency, and the other one is called sequential improvement. Sequential improvement is more general than sequential consistency, and we're going to focus on this one. There are rollout algorithms that have the sequential improvement property, but not sequential consistency. And importantly, model predictive control, the model predictive control context is one of these cases. But let's first say, what would we mean by sequential consistency? We say that the base heuristic is sequentially consistent if at a given state it chooses a control that depends only on that state and not on previous states, how we got to that state. More precisely, it has the following property. If the heuristic starting from state xk generates this sequence, then after you move to state xk plus 1, we generate by the base heuristic the tail of that sequence. In other words, a sequentially consistent heuristic does not change its mind, and after it goes to xk plus 1, starts choosing some different sequence. It stays the course. It stays with the trajectory that it generates. So that's what we mean, but by it applies the same control at the same state, no matter how we got to the state. And it's easy to see that if the base heuristic is implemented by some legitimate dynamic programming policy that uses a control mu case of xk at state xk, then it is sequentially consistent because that's what a policy does. And it's also possible to show that this is an if and only if statement. So the sequentially consistent base heuristics are the ones that are represented by legitimate dynamic programming policies. And for practical examples of sequentially consistent heuristics, greedy heuristics are of that type. And an example of a greedy heuristic is the nearest neighbor heuristic for the traveling salesman problem. It depends on that state, but not exactly on the precise sequence that it got to that state, the state being a partial tour for solving the problem. But we will focus on sequential improvement now, which is less restrictive, more general.
Professor?
Yes.
Can I compare sequential consistency with the general example you gave in the initial classes, where you're trying to go from Boston to Phoenix through St. Louis?
Yeah.
Can I compare that with sequential consistency?
Okay, going from Boston to Phoenix through St. Louis is a problem, but what is the heuristic that you use? If it is the nearest neighbor type of heuristic, you go to the nearest city, okay? Or some set of nearest, it may be sequentially consistent.
Okay.
So you can think of it in the context of that travel problem. In fact, it's convenient to think of it in the context of that travel problem, but there are many different heuristics that you can use in the context of that problem. Like for example, find the shortest route that goes through Chicago. Okay, that's also one possibility. There are many different types of base heuristics that you can use within this context. So I hope I have answered your question.
Yes, thank you.
Okay, so we covered sequential improvement, and now we're going to look at something more general, which is the sequential improvement condition that guarantees this cost improvement property. That's what we want to guarantee. We want to prove a theorem that says that if this condition is satisfied, then we have improvement from going from base to rollout. So what's the definition of the sequential improvement condition? It requires that the best heuristic Q factor is less than the heuristic cost for every state xk. Now the notation used here is hk of xk is the cost of the trajectory generated by the heuristic starting from xk. So you run the heuristic from xk, it gives a certain trajectory. The cost of that trajectory we denote by hk of xk. Now, what is the left-hand side? You will recognize for every given u, this term here as the q factor corresponding to u. So what this says is that if you calculate all the q factors and find the minimum one, then you are going to obtain a cost in the corresponding trajectory that is better than the cost of the heuristic starting from xk, better or equal. Okay, so let's interpret this condition in terms of this figure here. At the typical step of rollout, we have reached this state x tilde k, and in the process of getting there, we have calculated the cost, the heuristic cost, starting from x tilde k. Now, once you reach x tilde k, you consider all possible controls, evaluate the q factors corresponding to each one, and you find the one that has minimum q factor, which is the cost plus the heuristic cost starting from x tilde k plus 1. So what this condition says is that this trajectory is better than this trajectory in terms of their cost. So why does this condition imply that altogether, after we run the rollout algorithm all the way to the end, we're going to obtain a smaller cost than if we just stop at the very first state of the base heuristic? So what this condition implies is that the cost of this trajectory, which is the current trajectory that goes at x tilde k and uses the base heuristic after that, is greater than the cost of this trajectory that deviates at this point and goes along the control of the minimal q factor. So what this condition implies that at every step, you're generating a new trajectory from rk to rk plus 1 to rk plus 2 and so on with a monotonicity property. With every step, the cost of the trajectory, the working trajectory that you have, is smaller than the one before or equal. Now, R0 is the cost of the base heuristic starting from x0. Rn is the cost of the rollout after we have reached the end. And Rn, therefore, is smaller than R0, and it's also smaller than all the intermediate trajectories. And that proves the result. This is a proof of this cost improvement property. And the thing to note here is also this figure also illustrates why sequential consistency implies sequential improvement, because with sequential consistency, one of these Q factors that you calculate upon reaching x tilde k is precisely this heuristic cost. So the minimum Q factor is less or equal to the cost of any one of the Q factors, including this one. So let me give you an example here in terms of the traveling salesman problem, and then you can ask questions. Are there any questions now that I should answer right now? Okay, so let's go to this traveling salesman example. You have seen this figure or something similar with different numbers, perhaps, in earlier lectures. And we want to find the optimal cost tour, the minimum cost tour that goes through the 4 cities, A, B, C, D, with going once and only once through each one. And we have formulated this as a dynamic programming problem. involving these states, starting at state A, going to partial tours, adding a state in every step. And we have included this, these numbers give the cost of each branch here, that's intercity travel cost, and we have marked them in black here along the branches. And we have solved this problem by dynamic programming, going backwards, and the red numbers are the optimal costs to go. And now let's consider the nearest neighbor heuristic. And you can verify that this is both sequentially consistent and also sequentially improving, as it should. And let's calculate the trajectories generated by this, by the rollout algorithm. R0 is the trajectory generated by the base heuristic. R1 after one step of rollout, R2 after two steps, and so on. So let's see how we do that. At state A, we at the initial state, we run the base heuristic, the nearest neighbor heuristic, and it gives us this trajectory, which we call R0. Then for the first step of rollout, we generate all possible next states. We go to each one and we calculate and we run the base heuristic, the nearest neighbor heuristic from each one. We get this one, we get this one, and we get this one. And the one that gives smallest cost is this one here, because it has cost 27, and this one has cost 28. So this is the one that wins, and this is the new trajectory. We switch from R0 to R1, and it has smaller cost. So we have reached this state here. We generate the two possible controls, and from each one, we run the base heuristic from this one, and we compare it with this one. And this one is better because it doesn't have a 20 like this here. So the next state is going to be this one selected by rollout, and the corresponding trajectory is going to be this R2 trajectory, which has smaller cost. Then we could go to the next state and so on, but this problem after the second stage becomes trivial because there are no choices. There could be R3 is going to have a cost equal to R2, and and R2 is the one that generated by the rollout, and I think it also happens to be optimal in this particular example. So that's the key thing. If you have a base heuristic that has the right properties, sequential consistency or sequential improvement, and the nearest neighbor heuristic has both of these properties, then you can view the rollout algorithm as generating sequences of trajectories, complete solutions, complete tours, each one with a better cost than the preceding one. It is cost improving from beginning to end and everything in between. Now, this intuition we're going to use when we're also in other contexts where we're going to discuss variations of the rollout algorithm. So are there any questions here? So let's now go into variations of deterministic rollout and extensions. We're going to discuss 2 or 3 variations. The first one we call simplified rollout. The idea is that there are too many Q factors, perhaps, to calculate at any given state, so we would like to make the number smaller. Let's assume that we have a base heuristic that's sequentially improving, so it has the cost improvement property. The simplified algorithm, instead of finding the minimal Q factor at a given state, it chooses any control that improves over the heuristic cost, has a Q factor that's smaller than the heuristic cost. In other words, at a state xk, we choose as rollout control any control that satisfies this inequality. We don't necessarily pick the minimum one, the one that has that gives us the minimum Q factor. Just any Q factor that crosses this threshold. Then, by the previous heuristic, by the previous logic that we have, again, we generate a sequence of trajectories with decreasing costs, and we improve over the preceding trajectory. Now, the motivation for all this is that we don't have to examine all Q factors and compare them. And this may save a lot of computation. In the prime example, there are many different examples where this kind of scheme is helpful. But a prime example is in multi-agent rollout. And I gave an example of that a couple of lectures ago, where the control space is enormous. It's finite, a finite number of controls, but a huge number, and therefore also a huge number of Q factors. We don't want to compare all of them. The reason why this number is huge is because the control has multiple components, one component for each agent. So if you have, let's say, 10 agents, and each one has 2 choices, the size of the control space is 2 to the 10, okay? And you can easily construct examples that are meaningful and useful, but the control space is humongous. Multi-agent rollout reduces the search space by looking at only a subset of controls. Instead of looking at all the joint choices of the multiple agents, it considers choices one at a time. And as a result, from exponential number of Q factors to compute, we have a polynomial number of Q factors to compute. And this logic here indicates that we maintain the cost improvement property, assuming sequential improvement of the base heuristic. Okay, a quick proof of this cost improvement property. This is the statement that the rollout policy, which we call pi tilde, and its cost, which we denote from at time k by jk of pi tilde, starting at xk, satisfies this cost improvement inequality. For every k in state xk, the rollout cost is smaller than the cost of the base heuristic. And the proof is exactly what I gave in the previous slide, because this property here, this requirement, still allows the proof to go through, namely that the sequence of trajectories generated has costs that are monotonically decreasing, and you start with the cost of the base heuristic, you end up with the cost of the rollout, and this monotonicity property is maintained and implies this inequality. So are there any questions here? Okay, here's another variation that's very useful in practice. In many practical contexts, you have multiple heuristics that seem good, okay? That they look suitable for use in the context of rollout. For example, some heuristics may perform very well from some parts of the state space, but not from others. And there may be some other heuristic that makes more sense to use in these other parts of the state space. So you may have multiple heuristics and you may not even know which one is better and from where, but we can combine them in the context of rollout as follows. Instead of running only one heuristic, we run all of them at each state that we encounter, and we select the result of the best, we choose the best results. In other words, we select to follow the best out of the trajectories produced. So this can be very powerful because the super heuristic may be much more effective than each one of these heuristics individually. Now you can view this super heuristic as a base heuristic for a rollout algorithm. And the important fact here is that if all the heuristics are sequentially improving, the same is true for the super heuristic. So if all of these heuristics satisfy the cost improvement property, the cost improvement property is maintained for the super heuristic. And how do we prove this? Well, we prove it by verifying that the super heuristic is sequentially improving. We verify its definition. So the sequential improvement proper condition for the M heuristics, our hypothesis is that each one of those heuristics, say M out of capital M, satisfies this condition. This is the sequential improvement condition for heuristic M. This is the cost that it produces starting from xk, and this is the minimal Q factor that it produces starting from xk again. So this is the sequential improvement condition for every one of these heuristics. And now in this inequality, let's take the minimum over M, okay? Minimum of this right-hand side give us this, which is the cost of the super heuristic starting from xk. The minimum over M of the left-hand side is min over M and then min over U. But then we can interchange the order of the minimizations, minimize first with respect to U, and then with respect to M. The result is not changed. And what we have is this. So taking the minimum of both sides with respect to M in this inequality and interchanging the order of minimization on the left-hand side, we obtain this expression here. But if we look at what we have, this is the cost of the super heuristic starting from xk. Remember, is the minimum cost that you get by running over all of them. And this is the minimal Q factor of the super heuristic, because the Q factor of the super heuristic is G plus the minimum of the heuristic cost from the next state. So this is the Q factor corresponding to UK for the super heuristic, and the minimum of these Q factors is less than the cost of the super heuristic. And this is the sequential improvement condition for the super heuristic. And this is the end of the proof. This is a legitimate proof that sequential consistency is maintained as you pass through the super heuristic, and therefore also the cost improvement property. Are there any questions about this reasoning? Okay, so we have seen simplified rollout, multiple heuristic rollout, and now let's consider the case, another case that addresses a situation where cost improvement does not hold. Let's consider an example where where sequential improvement does not hold, and we do not have cost improvement as a result. So in this example, we have two stages: an initial state x0, two intermediate states x1 star and x1 tilde, and two final states. And there are two controls at x0, two controls at x1 star, and one control at x1 tilde. Now, okay, the structure here is such that this particular transition is high cost, okay? And the other important thing about this example is that we assume that the top path, x0 U0 star, X1 star, U1 star, X2 star. This trajectory is the optimal trajectory, the unique optimal trajectory for this problem, okay? Because this is a small cost and okay, whatever it is. We make the assumption that the numbers are such that this is the optimal trajectory. And now suppose that the Bayes heuristic, by accident or whatever reason, produces this optimal trajectory starting from X0. So if you start it at X0, it generates this trajectory, which happens to be optimal. How do I do that? Well, okay, it happens by accident, let's say. And the Bayes heuristic can be anything, right? It can be any control assigned at any state. So it's possible, certainly, to generate by accident the optimal trajectory. Now, what will the rollout algorithm do at X0? It will consider one control and the second control, and then run the heuristic from each one. Now, the heuristic at X1 tilde has no choice but to bring you to X2 tilde. So one trajectory corresponding to one Q factor, the Q factor corresponding to U tilde 0 is this one. Now, if we choose X0 star and get to this state, we have to run the Bayes heuristic from this one. But suppose that the Bayes heuristic, except again by accident or by design, chooses this red branch to go and goes to X2 tilde. This is the high cost transition. And we assume that it is chosen by the heuristic at state X1 star. And because this is high cost, it violates sequential improvement because this trajectory, this Q factor is high, and this Q factor is worse than the cost of the Bayes heuristic. So the rollout choice is going to be this one. And also the Q factor of U0 star, because the Q factor of U0 star is greater than the Q factor of U0. So the rollout algorithm will select this U tilde 0 and move to the non-optimal state. So the Bayes heuristic goes optimally, the rollout algorithm deviates and takes the wrong turn and gives us a worse trajectory. And what's happening here is sequential improvement is not satisfied. The Bayes heuristic gives smaller cost than all the Q factors. So in the absence of sequential improvement, the rollout algorithm can take the wrong turn. It can deviate from an already available good trajectory. This example also suggests a remedy for this situation. We keep track of the current best trajectory that we have found. And even if the rollout suggests following a different but inferior trajectory, we reject that and we keep following the current best trajectory. So we already have a trajectory and the rollout algorithm suggests some additional trajectories, but all of them are worse. In that case, we continue to follow the previous best trajectory and we avoid following the inferior trajectory suggested by rollout.
Professor, can I ask you something here?
Yes.
So I know that here the rollout is giving us a worse option, but it's actually depending on the heuristic itself, right? Because that the wrong choice, that red curve was suggested by the heuristic itself. So does the like the performance of the rollout depend on the performance of the heuristic that we are choosing, right?
Of course, yes. Yes. And this example is designed so that the Bayes heuristic is kind of weird. And even though it starts optimally, it takes the wrong turn. It's not sequentially consistent. It doesn't stay the course. It
Yes.
deviates from itself. And it violates also the sequential improvement condition. So this is a counterexample. It's designed to illustrate what can happen if you don't have the right condition, and so that you can expect cost improvement. Does that answer your question?
Yeah, so that means like a rollout cannot actually deteriorate the result that is obtained from the whatever heuristic that we are using, right?
Yes, in order to guarantee that, you have to verify that sequential improvement is satisfied or something similar.
Yes, that makes sense.
Any other questions? So this example suggests a fix. So now we're going to formalize this fix and apply the fixed algorithm to this example. This is called fortified rollout. Fortified in the sense that we add some features to it so that it doesn't go wrong in situations like the one of preceding example. It restores the cost improvement property when you have a base heuristic that is not sequentially improving. Now, this fortified rollout applies with any base heuristic and fixes it. It's a very simple fix. And the fix is you keep track of the best trajectory that you have obtained so far. And when the rollout tries to push you in the wrong direction, you reject its advice. So that's the idea. At each step, follow the best trajectory that you have computed so far. And the way you mechanize that is, in addition to the states that you have visited so far, these are permanently part of the rollout trajectory. Let's call this the permanent trajectory up to the current state xk. You also maintain another trajectory, which is end-to-end. And it is the best trajectory that you have found so far in the context, in the process of calculating various applications of the context of various applications of the heuristic. So here's the algorithm. At state xk, you assume that in addition to the permanent trajectory, you also have a tentative best trajectory, which involves beyond xk, control uk bar, and also a trajectory that takes you to to a final state, which we label like so. So we maintain this trajectory, and now at xk, we apply rollout. We apply all the different controls, we calculate their corresponding Q factors, and we find the one that has the minimum Q factor. And let's say it's this green control here. This has the best Q factor over this, over that, and so on. And now we take this trajectory and we compare its cost with the cost of the tentative trajectory, the best we have found so far. And if it is inferior, we reject it. And we keep following this control, the red control suggested by the tentative best rather than the green control. So that's what this bullet says. We reject the minimum Q factor choice if its complete trajectory is more costly than the current tentative best trajectory. Otherwise, we just accept the green control, the suggestion of the rollout based on comparison of Q factors, and we adopt this trajectory now as the new tentative best. And we have obtained cost improvement. From every tentative best trajectory that you generate is an improvement over the preceding one. And in the end, you get one that's better than what you obtained at the beginning using the base heuristic. The initial tentative best trajectory is the one given by the base heuristic starting from x0. So this is a very, very simple fix, and it fixes everything. Now, fixing everything does not mean that you're doing well. It simply guarantees you that you're not going to end up with a trajectory that's worse than what you started with. In order to get a good final trajectory, you not only need to improve the cost, but you need to improve the cost by quite a bit, okay? You need good performance. And that depends on the quality of the base heuristic. But this will provide some insurance that if you have a base heuristic that's generally good, but sometimes it can go wrong, then because of the lack of sequential improvement, then this fix of the fortified rollout will make things right again. Are there any questions here? Okay, so now let's illustrate the fortified algorithm for the example that I had in the previous, in two slides back. Remember, we have this two-stage problem: initial state, states x1, states x2, and the best, the optimal solution here, the optimal trajectory is the one at the top. And by accident, it is generated by the base heuristic starting from x0. So we go to rollout. Rollout will go over here, and then we'll follow the base heuristic. Now, the base heuristic, because it violates sequential improvement and follows this red branch. And so it calculates this Q factor, and both of them give you trajectories that are worse than the tentative best. So the choice, which would be the wrong choice of the rollout algorithm, is rejected in favor of maintaining the tentative best trajectory. So that's what these bullets say. The optimal trajectory is generated by the base heuristic at the initial state. In the first rollout step, we compute the Q factors of U0 star and U tilde 0 by running the heuristic from X1 star and from X1 tilde. And even though the rollout prefers U tilde 0 to U0 star because of this high cost transition, it discards U0 tilde in favor of U0 star, which is dictated by the tentative best trajectory. So this fortification has fixed the problem for us in this particular case. And then, okay, this is a two-stage example. If we had a many stages example, we would do the same thing at every step. We would maintain the tentative best trajectory, and we would reject the advice of rollout if it does not improve on the tentative best. So are there any questions here? So we have considered three variations of rollout without truncation. There are also other variations that involve truncation, other variations that involve limited simulation when it comes to expected, when it comes to stochastic problems. And all of these things can be combined in different contexts, including contexts of policy iteration, Q-learning, as we will discuss later in the context of infinite horizon problems. So here's another variation now, a model-free variation of rollout, which applies to problems where we don't have, we have a computer model, but not a mathematical model of the problem. And we're going to consider it in the following context. In the context of the general discrete optimization problem, where we have m variables, u0 up to un minus 1, that all enter into a cost function, a general cost function G. That's the problem we want to solve. We have already discussed that we can formulate this problem as a dynamic programming problem where we pick the components of the components of the solution one at a time, first U0, then U1, and so on. And with the state being the current partial solution. So from U0, we go to the state U0, U1 with choice of U1, then U0, U1, U2, and so on. So coming down from the initial state, some artificial initial state, we go down after k steps. We end up with this partial solution. And we want to apply a rollout using some base heuristic. But here's the problem. We don't know G, and we don't know the constraints of the problem. So we can't use the usual calculation of Q factors. What we assume instead is that even though we don't have a mathematical model, we have a computer model that will do all the work that's necessary to apply rollout. In particular, in rollout, what we need to do is generate all the possible next controls that satisfy the constraints, and then run a base heuristic from each one up to the final choice of U tilde n minus 1. Then at the end of each one of those circles here, each one of those nodes, I'm going to have a complete solution. And then what I need to have is some way to rank the solutions, to say that this one has smaller cost or larger cost. In other words, we need some software that will rank complete solutions. If we have a computer model that implements a base heuristic and enforces the constraint of the problem and also generates trajectories in some way that's internal to itself, but perhaps is hidden from us, and that will generate complete solutions that can be given into another software, which we call the expert software, that ranks the complete solutions. Then the expert will give us the branch that's best. And then we select that branch and go to the next node and do the same thing. Run the base heuristic, the computer version of the base heuristic, then run the expert to rank the solutions, and so on. So here's what we do. We do not know G. We do not know the constraint sets, but instead we have computer software that will do the following for us. Given a partial solution, U0 to UK, this software outputs all the next controls that satisfy the constraints and generates from each one a complete solution. Picks U tilde k plus 1 and completes the solution all the way to the end. Then we have a software expert or a human expert that can rank any two complete solutions, eyeballs them, any two of them, and selects the one that's better. In this way, it can rank all of these solutions. Basically, we need only the one that has smallest cost, and that will give us everything that we need to apply deterministic rollout. We have all we need. So that's another convenience afforded by rollout. It can be implemented in model-free fashion far more easily than other algorithms, like the Q-learning algorithm, for example, that I gave last time. This is a rather simple type of implementation. And with some colleagues, ASU colleagues, Peter Sulk, Julia Pedrielli, and Bengaloo, Eric Poppleton, and we have implemented this algorithm for the problem of RNA folding. RNA folding, where we have a sequence of nucleotides in the context of computational biology, and we want to figure out how nature folds them to create an RNA, molecule. The problem is that there are no mathematical models for RNA folding. There are software that will do that biologists use, and there are also expert software that rank different solutions. And so this is an ideal situation for a model-free implementation. And I will refer you to that paper, which is, you'll find it in the references to this class. And you can see on a very challenging problem how this model-free implementation of rollout has been mechanized. Have any questions here? Okay, so we have considered several variations. Now let's take a break before we go into stochastic rollout, rollout for stochastic problems. One variation that we did not consider is rollout with multi-step look ahead. So if you wish, you can think about how to implement deterministic rollout with multi-step look ahead. We've looked at one-step look ahead minimization so far. Multi-step look ahead involved generating all the states at the end of the look ahead and running the heuristic after that and calculating Q factors and selecting a control and so on. And also think about the computational issues, the computational difficulties in this kind of scheme. So we will take a break now and come back in 15 minutes. Are there any questions so far? I'll give you one more chance and you can come back with more questions at the end of the break. Okay, so we'll get back in 15 minutes. Okay, we'll be getting back. Before we get to this challenge question, are there any questions about the first half of the lecture? Okay, since there are no questions, let's go into this question of multi-step look ahead. Everything we discussed so far with rollout, simplified rollout, fortified rollout, model-free rollout, all of this was for one-step look ahead. What would happen if there are multiple steps of look ahead? We're showing here only 2 steps of look ahead. How would the algorithm work? Any suggestions? And also, what do you think is the main computational difficulty here?
So, Professor, can I answer? Try.
Yes. Go.
Yeah,
yes,
so
please.
Can I use the heuristic as a terminal cost approximation and run dynamic programming from the state k plus 2 till the state k, so that I get, and then I apply the first control U1 at the
yes. Yes, this is exactly right. This is the standard form of rollout without any approximations, no simplifications, and so on. What would be the main computational difficulty here?
It's that you're at each stage, you're exploding the states, like the branching of the states.
Yeah, if the branching factor here is large, then with a number of, with each stage of look ahead, there's a corresponding increase of the number of states. So the computational requirements increase exponentially with the branching factor, with the size of the look ahead. However, this is a deterministic dynamic programming, right? It's like a shortest path problem. So that's good because deterministic dynamic programming is much faster, can tolerate larger dimensionality than stochastic dynamic programming. So that works in our favor. But the main computational difficulty is the exponential explosion of the number of states with the size of the look ahead. Notice, however, that there's only one initial state here, okay? We don't run dynamic programming for all the states, just for the current state. Still, however, our multi-step look ahead, our dynamic programming minimization that you just mentioned is too time consuming. We may not have time to carried out online. So what would be remedies for that case? This is exact rollout of multi-step look ahead. Are there any approximations that will help? How about simplified rollout? In simplified rollout, we don't evaluate the Q factors of all of those sequences, but we do it only for some, enough to improve on the cost of the base heuristic, or running the heuristic from here. So if you had, for example, a multi-agent type of problem, or some problem that's amenable to simplification of the look-ahead minimization, then this dynamic programming problem may be simplified a lot, and you may be able to reach higher levels, longer levels of look-ahead. The fortified version of rollout also applies here. You maintain a current tentative best, and if you rollout algorithm, however you apply, does not give you something better, you discard the advice of the rollout algorithm. So basically, all the tricks of the one-step look ahead apply to multi-step look ahead for the purpose of addressing the computational difficulty of doing finite horizon dynamic programming, but over a longer horizon. Any other comments on this? Okay, so now we will go into the second half of this course that has to do with rollout for stochastic problems. And for this, we will use a clip from last year, a video clip from last year. And I'm going to pause the clip at various stages and ask for questions. So let's see if I can manage that now. Stochastic rollout and Monte Carlo Tree Search. Okay. Now in stochastic problems involving rollout, again, you have one-step or multi-step look-ahead minimization. You have approximation of the, you have an approximate cost function at the end that's derived from some base policy. And you have this minimization, one-step or multi-step, which defines the rollout control to apply at state xk, and the rollout policy. The only thing that's different is the expected value here over the uncertain quantities. And we're going to focus on the case where this expected value is not calculated in closed form, but rather is calculated by Monte Carlo simulation. If you use Monte Carlo simulation also, it's not only this expectation over this expression here that you are considering, but also you can calculate the cost of the base policy from the state, the final state of this look ahead, by simulation again. So simulation is used both for the L steps and also to calculate the values of the cost values of the base policy. And now that's a big problem. That's because this Monte Carlo simulation takes a lot of computation. Okay, so now back to the definition. There is a certain cost improvement result, which says that if the base policy is a legitimate policy, it's sequentially consistent, and that's the only kind that is worth considering in the case of stochastic problems. So we have a policy that gives an action, a control for every possible state and stage, and you use that to generate these cost function values. If you do that, then you have cost improvement. Starting from any state and any stage, the rollout policy has a smaller cost than the base policy. And the proof of this is essentially the same induction proof as for the deterministic case, which I think I gave in the previous lecture. So you do have some, you don't have this cost improvement property. Of course, this assumes that there is no truncation, okay, and no terminal cost approximation. So it holds under some idealized conditions. Also, this approximation, this value is not going to be exact because of simulation error. So in practice, this cost improvement property holds within some error bound, which is not easy to calculate. Now, the big issue here is how do we save in simulation? Because the simulation here is daunting for every possible control. And let's even focus on one step look ahead. For every possible control, you have to do Monte Carlo simulation. Lots and lots of sample trajectories to average, okay? And it's easy to see that this simulation can be very time consuming. It can be parallelized if you have Monte Carlo simulation is very well suited to parallelization, having parallel hardware. On the other hand, it's still a lot of computation. So that's the big issue here, and we're going to focus on that. But first, let's look at an example, an application, the original rollout application, so to speak. It involves a game of backgammon. I talked briefly about that in the first lecture. Backgammon is a game of skill and strategy, and also chance, because it involves rolling the dice. It involves two players, the black player and the white player, which have these pieces here on the board, and they move in the opposite directions. And okay, there are certain rules that guide the movement, and also when one player wins over another. There's no draw here. Either one player wins or the other player wins. There's no tie. What is the state here? Well, prior to every movement of pieces, there's a roll of the dice by either the black player or the white player. So let's assume that we are at the white player's turn, and the state is the board position and also the roll that this white player has rolled, okay? Like 6 and 4, or 1 and 3, or whatever. Now, given the roll of the dice and the board position, we can generate all the successor positions, all the possible successor positions that correspond to different ways of playing the role that you have. And now Tesoros' idea was, from each one of those positions, run Monte Carlo simulation with some backgammon player, roll out the game. That's where the word rollout came from. Roll out the game, but this is a game of chance. So the rolling out had to be done with Monte Carlo simulation. There is a cost of +1 or -1 only at the terminal position when one player wins or loses. There are no intermediate costs. So you got to run all the way to the end, the game, and then average the scores, and that gives you a number. That number is the score of the position. It can be viewed as some kind of probability of winning from that position. And the algorithm selects the play that leads to the position of highest score for that player. That's the way the Tesoros scheme worked. And the player that was used to roll out the games was another program called TD Gammon, which was an earlier program that Tesoro had developed based on approximate policy iteration and a method of temporal differences, which we will not explain in this lecture. So there was a neural network that was trained to generate moves at given positions and roles, and that's the TD Gammon player, and it was used to roll out games for both players, for both sides. Also, because some of these trajectories to finish the game were kind of long, truncation was used at the rollout. And the truncation involved cost function approximation at the end, which was again provided by TD Gammon. Now, TD Gammon played a pretty decent game, not quite at the level of world champion, but close to it. But this rollout played much better. Okay, it was extremely good. In the backgammon community, in fact, people think that a rollout player is the optimal player. That's not true, okay? It's still suboptimal, but it plays so well that people think that it is optimal, exactly optimal. Now, the problem with the rollout backgammon player was that it took an awful lot of simulation time. So for a given roll, there may be like 20 positions or so, okay? I'm guessing here, 15, 20, 30 positions that are possible. And from each one of those, you have to run hundreds of games, okay? And that's a lot of Monte Carlo simulation. And given that this work was done in 1996, it took an awful lot of parallel computing power to get any results. Even now, I could not find a rollout player on the internet that, that could play sufficiently fast to have a game with you. There are a lot of players based on neural networks, like the TD Gammon, like the sons of TD Gammon. There's several of those on the internet, and you can play against them. And they will generate moves in seconds, almost instantly. So that's the backgammon example. Very impressive at that time, very motivating, and also highlighted the difficulty with excessive simulation time. Now, Monte Carlo Tree Search is one of the methods that can be used to alleviate the simulation problem. One way to reduce the simulation requirement is using truncation, okay? Monte Carlo Tree Search is a different way to do that. Any questions? Okay, the motivation is to save simulation effort. So far, we have assumed that equal effort is made to evaluate the Q factors of all controls at a state xk, equal amount of simulation. In fact, in Tesoro's program, it was an equal amount of simulation. The number of trajectories was the same for all possible plays. On the other hand, we may try to be more clever than that. In particular, some controls may be clearly inferior to others and may not be worth as much sampling effort, as much simulation. We may not need to calculate the Q factors of these controls very accurately, because after a few simulation runs, they look so bad that, okay, we don't want to bother with them. Also, we may have some kind of heuristic criterion to decide which controls are clearly inferior. So that's one game that we can try to play. Also, just as some controls can be clearly inferior, some controls may also appear to be promising. On the basis of some limited simulation, they seem to have nice Q factors. So they're promising, they may be worth exploring better through the use of multi-step look-ahead, okay? So that's another idea involved in Monte Carlo Tree Search. It can be viewed as a randomized form of look-ahead, where we explore the look-ahead tree with different, based on some kind of randomization, based on some criteria. In particular, adaptive simulation is a term that's being used here. Simulation effort that's adapted to the perceived quality of different controls. That's what adaptive simulation refers to. And in doing adaptive simulation and exploring some controls more than others, we may try to balance exploitation and exploration. This is a classical trade-off that people talk a lot about in reinforcement learning. In this context here, exploitation refers to extra simulation effort on controls that look promising. Try to exploit the potential of these controls. Exploration refers to exploring adequately the potential of other controls. For example, we want to make sure that we don't neglect any controls that may look on the surface to be not so good, but on closer examination, they may turn out to be more interesting. And if we were to do more exploration, then we might discover their potential. So that's you have a thumbnail, some of the basic characteristics of Monte Carlo Tree Search. And let me also make one more point, because there's a lot of confusion in the literature about that. People think that Monte Carlo Tree Search improves performance. That's not what it does, at least in the context we are discussing here. It just tries to save in simulation effort. Of course, if you save in simulation effort, that means that you can devote more effort to other parts of the algorithm. So in that sense, it may improve performance. But by itself, the best performance out of rollout is obtained by doing exhaustive simulation. The more simulation you do, the better Q factors you're going to obtain, and the more informed decisions you're going to be able to make on the basis of these Q factors. Okay. So let's look at this landscape a little closer. Let's look at one step look ahead. At the current state, we consider various controls. Here in this picture, we have 3 controls. We simulate sample trajectories to the end. These are sample Q factors. And these are samples of this expectation here. For particular state control pairs, we obtain a sample, okay, by simulation, a sample of this. If we get enough samples, we can average them and get a close approximation to the expected value. So let's assume now that there are a finite number of control elements. We'll denote them by 1 up to m. And suppose that we simulate trajectories here, and each time we decide we're going to simulate this control, or we're going to simulate that control, or we have neglected this control, let's simulate that, okay? How do you decide which control to simulate? So suppose that after the nth sample, the nth sampling period, we have QUN, which is the empirical mean of the Q factor of control U. Now, what does that mean? This means value of Q factor, total sample value, divided by total number of samples. So it is the running average of Q factors corresponding to U and the state that you are, okay? Now, we want low values of that. If this value is low, that indicates that U is a good control. And we view this as an index for exploitation, an index about the potential of control U, a numerical value. So we do the simulation and we get exploitation indexes for these controls. Some of them are going to be high, some of them are going to be low. How do we use these exploitation indexes, the running indices, to select the control that we're going to sample next? That's one of the things that Monte Carlo Tree Search does. It decides which particular control to explore with simulation. And one way to do that is on some kind of statistical test. Bear in mind that none of this is very precise. There's a lot of voodoo stuff that goes on here in this area. And people will draw conclusions from one problem and apply them to a different problem. But this scheme that I'm going to describe makes sense and is also widely used. So, from the previous slide, we are at a given state. We have generated n samples, and we have exploitation indices for each one of these controls. However, the problem is that some of the other controls that may have bad exploitation indexes may not have been explored sufficiently. They may not have been allocated a sufficient number of simulation samples. So Monte Carlo Tree Search tries to balance the two: sample controls with a small sample count and sample controls that seem most promising. And a popular strategy is to introduce, in addition to the exploitation index, an exploration index, which indicates to what extent a particular control has been, the control U has been sampled, has been explored. And people have different formulas for this exploration index. The formula for the exploitation index is pretty clear. It's the running average of Q function values, Q function samples. The exploitation index, a lot of people have different proposals. And there are statistical considerations, statistical tests, confidence interval type of tests. And the RUN depends on the sample count of control U. And an analysis that figures prominently in this area is the analysis of multi-arm bandit problems. It's a particular type of dynamic programming problem where the trade-off between exploitation and exploration becomes particularly vivid. And for arm bandit problems, people have developed rigorously a rule, a confidence interval-based rule for setting the exploration index. This is called the UCB rule, upper confidence bound. And the formula is this expression. Depends on the number of samples. It depends on SU, which is the sample count of control U. And it depends also on a constant. And the multi-arm bandit analysis suggests C equals square root of 2. However, people play around with other values also. Assuming normalization, there are a number of rationales here for selecting C and also for this formula. Upper confidence bound rules have been extended to multi-step look ahead. There's another rule called UCT, upper confidence tree bound, something like that. However, AlphaZero uses Monte Carlo Tree Search and does not use any of these. Uses something different, again based on heuristics, semi-heuristics, some things that make sense, some that are kind of voodoo, mysterious. I would trust, of course, the alpha zero rule very much because of its apparent success. But why they have picked this particular formula, which you can find in their paper, is not very clear, nor do they explain fully. Needless to say also that this formula here, this UCB rule, is based on multi-arm bandit problems, but it's applied to other problems that are not multi-arm bandit, that have different characteristics. So is this legitimate? Okay, seems to work for many problems, but I would also not be very trusting in the validity of these rules here, or that they represent some kind of absolute truth. In reality, Monte Carlo Tree Search works very well for some problems where it's well suited, but there's no guarantee that's going to work on your problem. So trust but verify is the motto here. Are there any questions? There are some other issues in stochastic rollout that we have not discussed, and you can find the discussion here and there. There is here we said that this expectation is obtained with Monte Carlo simulation. But in Monte Carlo simulation, there's a significant issue having to do with variance reduction. The average that you get based on simulation samples may have large variance or small variance. How you do the simulation can play a big role in reducing the variance. And you can save simulation effort by using variance reduction techniques tailored to this context of stochastic rollout. We're not going to get into the details, but I want you to be aware of the fact that there's more than meets the eye and that we have covered in this field. And with that being said, I'm going to go to the last topic. Let me pause the video here. Are there any questions about Monte Carlo Tree Search and the segment that we just concluded? Okay, since there are no questions, we'll keep going. Which is a different kind of problem. Infinite spaces problems, including infinite control space. And these are the kind of problems that arise in control theory, control applications. In the classical control problems, the control spaces and the state spaces are continuous, typically vectors in Euclidean space, and they evolve according to a discrete time equation or a continuous time equation. Two of the most prominent types of control problems are these: the regulation problem and the path planning trajectory following type of problem. You may have seen this particular example. It's very popular, particularly in academia, but you can also try it yourself by balancing a stick on your finger and or in this particular picture, balancing a pole that has a mass at the end in the upright position by moving a car to sort of compensate for the moves of the pole the tendency to fall over this unstable equilibrium at the upright position. So if the upright position corresponds to the origin, a zero of the problem, okay, the control is the force that you apply on the car, and there is a systems equations that you can write here, differential equations, and there's an interesting control problem. It's interesting not because it has many applications, but because it's kind of cute and easy to understand and still quite complicated. So that's an example of a regulation problem, keeping a system around the origin or around a set point. Very, very common problem that dates to more than 100 years, since Maxwell's time, actually. Another problem is instead of keeping the state of the system near the origin, keep the state of the system around a given trajectory, or even designing the trajectory like an automobile wants to move from point A to point B, but there may be some constraints. The constraints may be velocity constraints. It cannot run too slow in some places, or too fast because it will get out of the track. There may be acceleration constraints, and there may be obstacles, like it has to stay on the road. And there may be moving obstacles also, something that's particularly vexing and requires online replanning, right? And there are these constraints, state constraints and control constraints. And the classical formulation of linear quadratic problems does not deal very well with state and control constraints. So that has motivated alternative methodologies. In particular, model predictive control has the ability to control systems while respecting state and control constraints in a reasonably efficient, computationally efficient way. I think I mentioned, I covered model predictive control in lecture 3. I'm going to discuss here just the principle on which model predictive control is based, and we're going to come back again to it in the next lecture. It is a general principle for dealing with deterministic infinite spaces problems, including infinite control space. So let's suppose that the system is running, we are at a state xk, and we're considering what control to apply out of the infinite number that is available. Now, the fact that control space is infinite means that the number of Q factors is also infinite. So we have to compare an infinite number of Q factors as well as compute them. Now, one possibility is to discretize the control constraint, but to do a good job of discretization may require a very large number of Q factors, so that may be inefficient. Now, here's the other possibility. Instead of discretizing and using some kind of heuristic in the context of rollout, it's possible to use heuristics that are based on optimization and look L-1 steps ahead. In other words, consider here a base heuristic that involves minimization over L-1 stages. So this is the base heuristic, an optimization problem that involves L-1 stages. And now you have also optimization of this cost of transition over UK plus the heuristic. So you can lump together, you can combine the base heuristic minimization, which is L-1 stages, with the first stage minimization, which is one more, for a total of L stages minimization. So a form of rollout involving a minimization heuristic is to look forward L steps and do a continuous space optimization over control sequences within this horizon. And we combine the kth minimization and the optimization heuristic into a single deterministic optimization. And now how do you solve this optimization, this L-step optimization? Well, that's what nonlinear programming does well, deal with continuous spaces over a limited number of stages. And that's what people have been using in this context, as well as in model predictive control. Use some kind of a quadratic programming formulation that takes into account the state constraints and the control constraints, as well as the dynamics of the system. There are gradient methods, conjugate gradient methods. There's a very well-developed algorithmic theory of optimal control problems that dates back to the 60s, okay? The 60s and even before that, which was developed in parallel with dynamic programming. In the 60s were a very active period for optimal control. You may have heard of Pontryagin's minimum principle. All of this research was fueled by the space program, getting a man to the moon, and getting spacecraft and satellites in orbit. All of this involved optimal control methods involving continuous spaces that were basically involving vehicle dynamics, Newtonian dynamics, which are, of course, continuous space formulations. So this methodology has been available for a long time and is still very, very potent and very useful today, and has been used in this context for solving these continuous spaces problems. And that's the idea that underlies model predictive control, and we're going to get to that in the next lecture. So that's the end of today's lecture. Are there any questions?
I don't have a question. I have a comment. It seems that the latest version of the lecture notes, the images are not showing, the figures are not showing, it's only the text.
Okay, good. So I'm going to correct that. I'm going to post the latest slides and the latest lecture notes. So look in an hour or so and they will be there.
Thank you.
Okay. I am stopping the video clip and going back to the last slide. Okay, so that's the end of this lecture. In the next lecture, we're going to cover model predictive control, some relations to rollout. The slides that we looked at, just a little, the last slides in the video clip had to do with general continuous spaces problems, and the issue of how you address the look-ahead minimization problem. This problem also arises in the context of model predictive control, but it also has, it's more specific within the context of that type of application. We're also going to discuss multi-agent problems and rollout for these problems. There is no homework for next week. What we're going to do now is we had 2 homeworks so far, and we're going to consolidate these homeworks. We're going to provide solutions that will be posted online, and we are going to organize some kind of tutorial or recitation around these homework problems. Make sure that that homework was understood. So that's our plan for next week. And you may want to watch video lecture 6 from the 2021 offering of the course. Are there any questions here?
Professor, can I ask a question? So it's regarding how you calculate the exploration and exploitation index. So I know that the path that hasn't been explored yet will have like a higher index for the exploration. But is that only it? For example, let's say if like 5 different nodes haven't been explored yet, will they have exactly equal exploration index in that case?
Well, if there are 0 samples that have been devoted to those controls, yeah, they will have equal exploitation index in lack of any other information. Once you start getting samples from these underexplored controls, then there will be a way to rank them based on the sum of the 2 indices.
Okay.
Or at least that's the kind of scheme that people have been using.
Okay.
That answer your question?
Yes, partially. Yes, thank you, Professor.
Any other questions? Okay, so we'll see you next week.